carry on.
Thanks. For those of you that don't know me, I came in a little bit late. My name is Mario Valdez, as Carl said. I'm an engineer in the Manufacturing Quality Division out at Los Alamos. And today we're going to talk a little bit about kind of what we do for CMM interim checking. So I just want to give you guys an overview of kind of what I'm going to be talking about. So I'm going to cover basically the introduction, background on the interim checking that we do, as well as kind of the design strategy that we came up with. After me, Josh is going to come in and explain kind of the procedure as well as some of the calculations from our interim checking that we currently do at Los Alamos. And Lucas is actually going to come out, finish up and round it off with some of the results and some of our future work that we have planned ahead. So let me give you guys a little introduction. Currently right now, all of our CMMs are basically on a 1-year calibration cycle. We have approximately 18. That's not including, I believe, a handful that are at our detonators production facilities. So any of ours range from any of our weapons component, nuclear, non-nuclear weapons components. Basically, we calibrate all of our CMMs to the ISO 10360-2, which is basically the acceptance and re-verification for CMMs on linear measurement. Well, the 10360-2 actually strongly recommends interim checking. So interim checking basically is kind of a verification of your process. So in our case, our instrument, in our case, CMMs. Typically, it's not really used much in industry because of the fact that it takes up quite a bit of time and time that could be used on production. So granted for us, since our production is kind of has a much smaller throughput, given the fact of the components that we make and manufacture out there, we kind of strongly recommend, we kind of follow what the 10360 recommended, and that's doing interim checking. Basically, the interim checking that we're using in the gauge, they kind of range from anything from calibrated ball plates, where you can basically look at a full parametric solution of your actual instrument, to manufactured test pieces. Basically, a test piece that if you have one part that you're measuring consistently, day in and day out, you can basically make a part, calibrate the part, and use that to basically do interim testing. And that's kind of nice because what that does is, in essence, is it's sensitive to the errors that are currently inside your measurement process. Nothing really deviates. You kind of capture everything that's kind of manifested inside of your measurement process. So thinking of that, we kind of went with an off-the-shelf gauge, which we call the machine checking gauge, sold by Renishaw. Basically, it was patented back in the late 80s, and basically what it does is simulates a large sphere. So here's the Renishaw checking gauge. Here we have an arm of a known radius, not calibrated, but of a known radius, and here we have a kinematic seat that sits here. And basically what this does is you have a probe that attaches to the probe of the CMM probe, as well as a kinematic seat here. And basically what it does is it collects a point, this distance, this radius distance from here, from this kinematic seat to this kinematic seat. That's the known radius of the measurement. Basically what it does is it just measures and simulates a large sphere. These are off the shelf, like I mentioned, not really very costly. You're looking at about $3,500. And total runtime for this interim checking is approximately 30 minutes. We tend to recommend that we do this once a week on all our instruments. So it really doesn't take up much machine time. Like I said, you do it once a week, kind of really checks, spot checks the health and some of the statistical process control.
So does it sit within those parameters that you showed, that Carl showed?
For
what are you looking for a result?
Yeah, so we're going to get into that a little further on. We actually have some results on that, and Josh will go over some of that. So why are we doing this? And it's recommended. So basically at Los Alamos, we do it because like all quality organizations, or all organizations that have quality, is basically non-conformance or NCRs. This is just kind of a small list of some of our NCRs that are related to our CMMs. So you can see some of them range from basic, software revisions, machine configurations, to out of tolerance, to temperature excursions. In essence, what we want to do is we want to try to identify, okay, is there a way that we can basically identify this early on in the measurement, in the calibration cycle, to figure out, okay, we're having an issue. Is there a way that we pinpoint these issues? And one way to do it is using the interim checking. And hopefully that's what the plan is basically use that. From there we can see maybe temperature excursions, out of tolerance, things of that nature. So just give you an idea, what are some of the influence quantities that basically contribute to possibly some of these NCRs, as well as some of the measurement uncertainty, anything that's inherent in the measurement process. Typically for CMM measurements, you broke it down into 5 categories. Basically you have the instrument itself, the environment the instrument is setting, the workpiece that you're measuring, the measurement strategy, and extrinsic effects. The measurement instrument itself, this is kind of what we're looking right here. Basically, this is the CMM. Anything that kind of ranges from the axes, the ranges, the scales, anything that, it could be any one of the 21 geometric errors that are inherent in this machine. If you have a rotary table, that's an additional 8 errors, and then you're looking at 29 errors total. The geometry, that's just from the instrument. That's not including probing, that's not including anything thermal or any of that nature. So that's kind of what measurement instrument. Environment is basically any of these effects that is going to, that where the instrument sits. So basically you're looking at temperature variation, radiance, humidity, vibration, cleanliness. Typically we can control these if you have a really well controlled environment HVAC system. The next thing we're looking at is a little harder. It's kind of a workpiece. Now we're kind of looking at, okay, form error, what's affecting that? Thermal expansion, the mass, the size. Are we getting sag? Are we getting droop? Is this thing deforming the table? Some other physical characteristics of the workpiece. I'm sorry. Then we're looking at the measurement strategy. This is things, the distribution of points, the software that's used to evaluate filtering, the probing method, things of that nature. And then here's another one here. This is a really hard one to characterize. This is the extrinsic effects. In essence, this is basically some of the factors that contribute to the irreproducibility of CMM measurements, and that are typically out of the manufacturer's control. These are the hardest ones to quantify. So we're looking at like temperature distortions, the distortions of the workpiece and the CMM itself. Operator, things change from operator to operator. Fixturing, are we putting too much stress? Do we have to do a finite element analysis to kind of quantify that? Clamping, orientation, these things, all these things basically affect the measurement result. And like I know, they're not exhaustive, so I mean there's a list of things that can happen. There's things that are unknown systematic effects that are usually quantified in the bias if you're using calibrated artifacts.
Excuse me.
Yes, sir.
In the workplace characterization, what is elasticity? I'm trying to think of elasticity as it relates to a workbench.
So elasticity is basically how elastic the part is. Is it compliant? Is it stiff? It's related to that nature. So typically when these instruments are probing, sometimes there's Hertzian forces that deflect. So basically, then we see kind of like a pocket in the measurement. So we're not typically probing the exact surface of the workpiece. We may be probing, I guess, a subsurface. I'm not really a surface guy.
You're actually touching the part, you're deforming it to a certain point where it doesn't reach plastic deformation, and it's always going to bounce back to its original state. If you ever reach plastic deformation, the curve's going to come back and you're going to have a different stress in the part. Now it's going to deform.
So that's called elasticity in your work.
Yes, we call it elasticity. Basically, it's a physical characteristic of the workpiece.
The other thing you have to consider, some of our parts are up like Montano, for example, softer material, and we have to watch burning force on the key.
Right.
Well, I'm only used to CNMs as used on printed circuit boards, and I've never heard elasticity being a factor in checking resistors, capacitors, and that sort of thing. We want to check and find out if it's the right part in the right place.
This is pretty much strictly a mechanical feature. It's not there's no electromechanical or electrical design. This is just pretty much a mechanical feature in the part.
And like Josh said, when you have a softer part, that kind of plays into a lot of these CMMs have low force probing, high force probing. It depends on if you're doing tactical, if you're doing scanning, continuous scanning. That all kind of plays in, and that all affects the measurement result. So yeah, so elasticity can definitely be an issue if you're measuring,
And
software.
part of it, part of that factor must be the ability to adjust the force of the
Exactly.
contact.
Right.
probe.
If we have too low of a force, well then the CMM won't trigger to take a point. So basically the CMM will come in essence to the surface and not trigger, and then we're not collecting the data point. So then if it doesn't collect that point, but it collects an exon, then we have a gap in our distribution.
And that's called elasticity.
No.
No.
That ties into the elasticity and the probing force. It gets really complicated really fast when you're looking at kind of some of these softer parts and some of these other materials. But that definitely affects our measurement results.
It's interesting how different disciplines have different meanings of the same words.
Right, exactly.
So in a medium rate or a high rate manufacturing facility,